In this video, we're going to be looking entirely at the function of the loop of Henle, which in my experience is the most confusing part of the nephron in order to understand. Now, the loop of Henle functions primarily to balance the amount of water versus the concentration of salt that exists within the filtrate that is eventually going to become urine. Now, geographically, within the nephron, we remember that the loop of Henle follows the proximal convoluted tubule, and in the proximal convoluted tubule, this is where the overwhelming majority of nutrients that were filtered out of the blood are reabsorbed back into the blood from the nephron, and this also includes a number of relatively specialized ions aside from sodium and chloride. Now, as a consequence of this reabsorption immediately before the loop of Henle, the solute concentration in the filtrate within the nephron is significantly lower than it was before, which plays a very important role in terms of what happens as we enter the descending loop of Henle. Now, the descending loop of Henle is the first time that our nephron structure enters into the renal medulla, which is a distinct type of tissue compared to the cortex. So glomerular pressure filtration and the reabsorption of nutrients and specific ions occurs within the renal cortex, which is on the outside of the kidney. And then for the loop of Henle, we descend into the renal medulla, whose structure is very important to understanding how the loop of Henle will function. Now, as a consequence of the nutrient reabsorption that happened in the proximal convoluted tubule, which results in a significantly lower concentration of solute inside of the loop of Henle compared to outside of the loop of Henle, this gives us our first hint about what type of reabsorption is going to occur in the descending half. Now, if we take a look at this situation, more specifically, if we look at the actual structure itself, if the inside of the loop of Henle has a lower concentration of solute compared to the tissues in the renal medulla that are found outside of the loop of Henle, we can conclude that the outside, the actual renal medulla tissues around which we find blood vessels for reabsorption, we can assume that this is the hypertonic side, while the inside of the loop of Henle is going to be the hypotonic side, which means that water we would expect to osmose, let's spell that properly, osmosis out of the loop of Henle, resulting in, again, water leaving the nephron and some of it remaining in the renal medulla, but a lot of this water is ultimately going to be reabsorbed by the blood. Now, as a consequence of this, as our water within the loop of Henle osmoses out, that means that if we pay attention to the concentration of Na+, as our solution volume, which is again based on water, decreases, by definition, the concentration of solutes within the nephron are going to increase as a result. Now, we know that diffusion and osmosis stop whenever we reach an isotonic situation, which means that the inside of the nephron and the outside in the tissues of the renal medulla have basically an equal balance of salt and water. And at that point, we would expect the osmosis of water to stop. But that's not actually what happens. The osmosis of water more or less happens continuously as we descend all the way to the bottom to the loop of Henle. So why exactly is this, even though this happens technically long past the point we expect this to be isotonic? Well, in order to understand this, that must mean that there must be a solute that is making the outside tissues of the renal medulla more hypertonic compared to inside of the loop of Henle, and that solute is this particular compound here, which is a compound called urea. Urea is a very important component of urine. This is actually the chemical that appears yellow and gives your urine a yellow color. So the more yellow your urine is, the more urea you have in it. And urea is a very important chemical in terms of maintaining the hypertonicity outside of the descending loop of Henle in order to guarantee that water keeps osmosing out. Where exactly does urea come from? Well, as it turns out, urea is a waste product that is the breakdown, or that results from the breakdown of proteins and the digestion of amino acids. This is basically the way that the body gets rid of nitrogen from the body, as this compound is soluble, so urine is a natural way to get this out of the body. So in order to understand what happens in the ascending loop, if we take a look at what happens to the solution volume in the descending loop, because we're losing a lot of water from the loop of Henle, the solution volume decreases, causing the inside solute concentration to increase and making the inside of the loop of Henle more hypertonic than it was before, meaning that our concentration of Na plus ions is going to get higher and higher and higher, ultimately leading to the point at which the concentration of Na plus is at its highest point around the bend between the descending loop and the ascending loop. Now, as a consequence of this, because we have a much higher concentration of Na+, starting at the ascending loop, which is where the loop of Henle goes up, we would expect that Na+ would diffuse from the loop of Henle out into the medular tissues, and some of this, again, is going to be reabsorbed into the blood of our peritubular capillaries, and that's exactly what we see happening in the medulla. As our filtrate migrates up the ascending loop of Henle, more and more Na+ is going to diffuse out. Now, just like the osmosis of water, all diffusion stops when we have reached an isotonic concentration, because eventually the concentration of Na+ inside of the loop of Henle is going to be relatively equal to the concentration of Na+ found outside. Now, we're not actually done here. As we get all the way to the top of the loop of Henle, before the distal convoluted tubule, we still transport Na+ out of the ascending loop of Henle and into the renal medulla. But if we've reached an isotonic concentration here, how does this transport of sodium continue happening? So in the top of the ascending loop, this is where we need the beginning of active transport, because at this point we need to move Na+ from a lower concentration to a higher concentration against the concentration gradient, which means that we need active transport and a constant supply of ATP in order to keep this going. Now, on the surface, this would be enough information, but there is actually one more subtle detail that actually explains how the entire system sustains itself, and it concerns the structure of the renal medulla, which is actually not a completely solid structure. It's actually relatively fluid, which means that solutes such as Na+ or urea, as well as water, are all able to move around relatively freely. Now, if we take a look at the two locations outside of the loop of Henle, so outside of the ascending loop first, because of the large concentration of Na+, we have created a hypertonic situation, and this Na+ does not want to remain together because all of their charges are repelling each other, and because they will naturally move to an area that is hypotonic in nature. Now, where do we find one of those? Well, if we look at what's happening outside of the descending loop, as the percent of the solution here that is water increases, that means that our concentration of Na+ here is going to get lower and lower and lower as the volume of water here increases, meaning we are creating a hypotonic situation. And because the renal medulla is not a completely solid structure, that means that this sodium can diffuse from outside of the ascending loop to the area outside of the descending loop, and this has the added benefit of keeping the outside of the descending loop hypertonic all the way through to allow water to keep osmosing out no matter where in the descending loop it is, because the sodium from the ascending loop diffuses over, thereby increasing the Na plus concentration over here and ensuring that water will only osmose in one direction. One other way that this has helped is that this water is naturally going to osmose to an area that is more hypertonic over here because there is less water over here compared to over here. And this counter-current movement, water and Na plus moving in opposite directions in order to naturally stabilize these concentration gradients, is what allows the descending loop to constantly osmose water out, because the Na plus from the ascending loop maintains a hypertonic concentration outside of the descending loop. In the next video, we're going to finish off the exploration of the different parts of the nephron, looking first at the distal convoluted tubule and its regulation of pH, and looking at the role of the collecting duct in order to stabilize the isotonicity of urine and making sure that the balance of salt and water in the urine and blood is exactly what it needs to be.